It's been more than a year since the James Webb Telescope, which had taken over 20 years to complete, was launched. And for such a relatively short time, the ultra-modern and most powerful in history piece of equipment has already made plenty of discoveries. By observing the universe at infrared wavelength, James Webb lets us see things no other telescope has ever shown before. The primary goal of this incredible piece of equipment is to study the formation of galaxies and stars that appeared in the early universe. For example, look at the closest to us stellar nursery, a region of space where new stars get born. NASA has shared an image from James Webb that shows a small star-forming region. If you look at the picture attentively, you'll see jets bursting from infant stars. Around them, different colored clouds of cosmic dust are colliding with one another. The view is mesmerizing. The red dust consists of molecular hydrogen. You can also notice that some stars have something like shadows. Those hint at the creation of what will later become planets. At first sight, the image may seem chaotic, but astronomers claim that it's a relatively small and quiet stellar nursery in comparison to some others. Many young stars there are similar in size to our Sun, or a bit smaller. The photo itself was taken with the help of Webb's near-infrared camera, NIRCam. It's the observatory's primary camera that snaps images of the cosmos in two different infrared ranges. Another amazing discovery the Webb telescope has made is smoke molecules in a distant galaxy. It's the first time such molecules have been discovered so far away from our planet. The galaxy in question lies 12.3 billion light-years away from Earth. It most likely formed about 1.5 billion years after the Big Bang. Despite such a huge distance between the galaxy and our planet, scientists have managed to detect chemical compounds found in soot or smoke, and it's quite a big deal since it has pushed the record for detecting similar complex molecules back by around 1 billion years. This study has also confirmed the sheer power of the coolest piece of space equipment of all time. It managed to make this discovery despite the fact that the spectrometer needed for the measurements didn't perform to the fullest after having experienced a sudden and surprising degradation. The James Webb Telescope has also helped to boost our understanding of exoplanets. Those are planets orbiting stars other than our own Sun. At the beginning of 2023, the observatory spotted its first exoplanet, LHS 475b. It's located 41 light-years away from Earth and is approximately the same size as our planet. According to NASA, nowadays, James Webb is the only operating telescope capable of categorizing the atmosphere of Earth-sized exoplanets. The research team behind the discovery believes such results underline the precision of the telescope. They hope that it will help us locate many more rocky exoplanets that we might be able to colonize in the future. Even though, at first sight, it may seem that the universe is pretty empty, it's actually a very busy place. And Webb has all the necessary instruments to see all kinds of cosmic events happening out there. Just look at this image of WR 124. It's a star on the cusp of its explosive demise. In the image, the star is about to go supernova. It happens when a star runs out of its fuel and explodes at the end of its life cycle, releasing a giant cloud of space dust and hot gas into space. The star captured by the Webb telescope was at the Wolf-Rayet stage of its life. That's a period when a star is shedding its outer layers before going supernova. The next amazing thing discovered by James Webb is a star-planet hybrid with very strange clouds. This bizarre world, VHS 1256b, is actually a brown dwarf. Those are bigger than planets but too small to classify as stars. They emit some light of their own and are quite hot, but their mass is simply not enough to fuse hydrogen into helium like full-fledged stars do. Space bodies of this kind aren't actually brown. They occur in a wide variety of colors, but those are mostly invisible to the human eye. What we can see is the light they emit, and to us, it appears to be dark orange or magenta. The brown dwarf discovered by the Webb telescope is almost 20 times the size of Jupiter. It orbits 2 red dwarf stars, and to complete one orbit, it needs over 10,000 years. Astronomers first found out about this unusual exoplanet in 2016, but at that time, they didn't classify it as a brown dwarf, and, thus, couldn't explain its puzzling reddish glow. Now, thanks to the James Webb Telescope, They know the space object's origin. Anyway, back to those clouds. As you know, clouds on Earth are made of water vapor. But those on the brown dwarf are different. They seem to be made of sand. It looks like good old sand from Earth, but it's actually not. The clouds are made of tiny particles of silicate. Another recent discovery involves several large galaxies that scientists believe were born not long after the Big Bang. They aren't supposed to be there, and no one expected to find them. But the James Webb Space Telescope has spotted them. These galaxies, as massive as our home Milky Way, are full of mature red stars. Astronomers have analyzed the light coming from them and estimated their age 500 to 700 million years after the Big Bang. It means that they came into being when our universe was very young, almost a baby. But the most bizarre thing about these galaxies is their tremendous size and the age of the stars dwelling there. The data received by the telescope don't coincide with the existing ideas about what the universe looked like and how it evolved in its early years. It also doesn't match the earlier observations made by Hubble. And here, James Webb has captured a distant region of space in unprecedented detail. This section of space is known as Pandora's cluster. In the image, you can see 3 massive clusters of galaxies coming together and forming a megacluster. The combined mass of these clusters acts as a powerful gravitational lens. And thanks to this natural magnification effect, scientists can see other galaxies in the region. Astronomers claim that the most recent image of Pandora's cluster is stronger and deeper than they have ever seen. James Webb has also managed to spot thousands of young stars never seen before in the Tarantula Nebula. This space formation got its nickname because of the appearance of dusty filaments spotted in previous images. It's the biggest star-forming region in the local group, which includes the galaxies nearest to the Milky Way. The Webb telescope's images have helped to shed light on the composition of the Tarantula Nebula. The telescope has also detected protostars, infant stars in the process of gaining mass. Astronomers expect that these protostars will eventually form and shape the nebula further. Among other discoveries made by the James Webb Telescope, you can see the birth of 50 distant stars. Some of them power protoplanetary disks, which might later form solar systems light years away from our own. Here's one more image from James Webb. You can see a supermassive black hole that has a mass of 9 billion suns. It's so ginormous and ancient that scientists are struggling to explain its existence. Astronomers have also discovered a distant ring of dust, rock, and gas that contains a chemical called methylcation. It's known as a molecular building block of life, and it makes most of the organic material on our planet. James Webb helped researchers see powerful sandstorms on a planet 235 trillion miles away. Astronomers were happy to discover this treasure chest of countless tiny sand particles. Now look at this. Do you recognize this image? Those are the so-called pillars of creation. But this new view shows us just how star-speckled that dusty region actually is. You can compare the new photo with the one taken by Hubble in 2014. This is astonishing proof of scientific progress.
Recently, the James Webb Space Telescope has unearthed a mysterious ancient galaxy, and it might completely change our understanding of the nature of dark matter and the process of galaxy formation. The telescope has managed to spot a stellar population bigger than our home Milky Way galaxy from 11 billion years ago, and it shouldn't actually exist. This galaxy is massive and is home to extremely old stars. They formed in the early universe. The problem is that this new observation upends our current cosmological models, since, by the time of the galaxy's birth, not enough dark matter had built up to seed such a formation. Researchers have been chasing this particular galaxy for 7 years. They spent endless hours observing it with the help of the 2 largest telescopes on our planet to figure out how old it was. Unfortunately, it was too faint and too red, so no one could measure it. Only after scientists moved their observations to space and started using the James Webb Telescope did they manage to confirm the nature of the galaxy. The thing is, unlike the Hubble Space Telescope, which orbits around Earth, James Webb moves around the Sun 1 million miles away from Earth. That's why it made it possible to see the galaxy clearer. Previously, astronomers were sure that in early cosmic times, there were very few huge galaxies. But recent findings challenge these theoretical models. Extremely massive dormant galaxies have been discovered as early as 1 to 2 billion years after the Big Bang and the beginning of the universe. The scientist who led the spectral analysis of the James Webb Telescope data said that they were doing everything possible to confirm the oldest galaxies that existed deep in the universe. When they did, it pushed the boundaries of the current understanding of how galaxies form and evolve. And now, the main question is, how they managed to form so fast in the early universe, and what enigmatic mechanisms made them stop forming stars all of a sudden while the rest of the universe was still doing so. Galaxy formation is largely dictated by the concentration of dark matter. You see, around 84% of matter in the universe doesn't emit or absorb light. Astronomers call this stuff, which can neither be seen directly nor detected by indirect means, dark matter. It supposedly affects visible matter, radiation, and the very structure of the universe. Finding extremely massive galaxies so early in the universe is posing serious challenges to our standard model of cosmology. All because astronomers don't think that such monstrous dark matter structures as the ones hosting those massive galaxies had enough time to form. Researchers need more time to figure out how common such ancient galaxies are and how massive they can be. But if they manage to find more of those, it will really upset our ideas of galaxy formation. But it could improve our understanding of the physics of dark matter. Bizarre ancient galaxies aren't the only thing discovered thanks to James Webb. For example, scientists have long suspected that supermassive black holes could have existed in the early universe, and this theory has been proven only thanks to the JWST and its infrared eye. It showed that an ancient black hole within galaxy Sears 1019 was actively munching on all the matter it could lay its hands on. This hole is from the times when our universe was less than 600 million years old. And that's another mystery we're yet to crack. It's supposed to take way longer than 600 million years for a supermassive black hole to grow to its full potential. Astronomers were watching the galaxy hosting the unusually old black hole as part of the Cosmic Evolution Early Release Science Survey. They saw the galaxy as it was when our 13.8 billion-year-old universe was just 570 million years old. Besides the ancient black hole, scientists spotted two other ones. Those probably appeared 1 and 1.1 billion years after the Big Bang. They also discovered 11 ancient galaxies that existed between 470 and 675 million years after the beginning of cosmic history.
The James Webb Space Telescope is about to begin investigating astounding light shows happening on one of the giants of the solar system, Uranus. These mysterious lights have been puzzling scientists for a long time, and for a good reason. The main goal of the $10 billion space telescope will be to explore in greater detail the processes creating polar light shows over different planets. Auroras are familiar to people on Earth. We have stunning northern and southern lights, which can be observed along the poles of our planet. They're generated when charged particles streaming from the sun's solar wind hit our planet's protective magnetic field called the magnetosphere. These particles then travel down magnetic field lines and interact with particles in the atmosphere of our planet, creating glowing lights. Auroras have been spotted over other planets in the solar system before. Theoretically, they should be able to occur around any planet with an atmosphere and magnetic field. However, not much is known about extraterrestrial light shows. Currently, we know very little about auroras on Uranus. This is an ice giant with an atmosphere that consists of water, ammonia, and methane. It was just last year, after 3 decades of investigation, that a research team confirmed an infrared aurora around Uranus. Due to a collision with a roughly Earth-sized space body that occurred in the past, Uranus is tilted at a 97.77-degree angle. In other words, its poles are oriented almost directly toward and away from the Sun, and its auroras are positioned around the area that would normally be the equator for any other planet in the solar system. Along with observing auroras on Uranus, researchers will also try to find the answer to an intriguing question. Are auroras responsible for keeping this icy planet warmer than expected? The temperatures of all the gas giant planets in the solar system, including Uranus, are hundreds of degrees above what they should be if these planets were only warmed by the sun. The big question is, what makes these worlds so much hotter than expected? One theory suggests that auroras could be the reason. They could generate heat and push it down toward the magnetic equator. James Webb is supposed to start its study of Uranus early in 2025. The telescope is going to capture images of the ice giant over a single planet's day. It lasts around 17 Earth hours. Hopefully, it will allow the research team to map auroras across a whole rotation of the magnetic field of the planet. Scientists also want to find out whether Uranian auroral emissions are produced when the magnetic field of the planet interacts with the solar wind, as it happens on Earth. Another theory states that charged particles might be coming from sources within the planet, similar to how Jupiter produces its auroras. On the largest planet in the solar system, charged particles trapped in the magnetic field around the planet spiral inward toward the north and south magnetic poles, producing auroras. Another aurora researching project involves gas giant Saturn. Astronomers are going to observe this planet's northern auroral region for an entire Saturnian day, which lasts 10.6 Earth hours. This will allow the team to monitor how the temperature in that region changes as Saturn rotates. By examining Saturn's atmospheric auroral energies for the first time, experts hope to find out more about the sources of charged particles driving the planet's auroras. Some of Saturn's auroras might be caused by swirling winds within the planet's atmosphere. This previously unknown mechanism of triggering atmospheric light shows hasn't been seen on any other planet before. Saturn is actually one of the windiest planets in the solar system, with wind speeds reaching almost 1,120 miles per hour near the equator. These powerful winds seem to be responsible for the planet's variable rotation rate, which makes it difficult for astronomers to figure out how long the day lasts on the ringed planet. Perhaps one of the most perplexing aspects of our solar system is the fact that not every planet is a lovely solid sphere like our Earth. Some are almost entirely made of gas. If you visited Jupiter, you wouldn't be able to stand on its surface. You'd likely fall through its gaseous layers, all the way down to the planet's core. You'd have to survive an incredible amount of pressure before hitting its potentially rocky core. Whatever the case, mysterious gas orbs have always intrigued scientists. Luckily, now they have the James Webb Space Telescope to satisfy their curiosity. The incredibly powerful infrared eyes of this instrument see much more than what the telescopes of the past could spot. And recently, a team of researchers announced they may have noticed something interesting about the dynamics of gas giant formation. All thanks to James Webb. Soon, we might be able to answer how long gas giants have to form around their parent stars before all the gas around those stars fades away. At the moment, it seems like this period of time isn't too long, but there are some nuances. The team used the Webb telescope to probe the disk wind. This name doesn't really refer to any kind of wind. Instead, it refers to the process of gas leaving a disk around a star. The so-called disk, also known as a protoplanetary disk, is filled with various stuff and has the potential to give birth to planets. Astronomers knew such disks existed and could play an important role in disk evolution, but they couldn't figure out the underlying physics or estimate how much mass was lost in the process. Now, they might be able to do so. The wind disk studied by the team seems to move at a rate of 6 to 9 miles per second, which is quite slow for something moving in the vastness of space. Fast-moving gas patterns, known as jets, can boast speeds of more than 62 miles per second. The researchers haven't come to any specific conclusion about how long gas planets have to form before depleting protoplanetary disk gas completely. But based on their preliminary calculations, it might take about 1,100 years. Even though it sounds like a really long time for us Earthlings, in astronomical terms, it's an incredibly short timescale. For comparison, a protoplanetary disk can live for 5 to 10 million years. One of the main difficulties in examining disk-wide movements is finding a protoplanetary disk. But our solar system doesn't have any. All our planets are formed and complete, including gassy ones. That's why the team found another target, a disk around a young, low-mass star called T-Chi. This star, lying 350 light-years away from Earth, is quite interesting in its own right. It has a large dust gap in its disk. It's thought to be created by a planet or planets, consuming all the material on its way around the star. Such a gap may suggest that the star has budding planets orbiting it. It's also old enough for those nascent worlds to munch on parts of the disk itself. It might be what we know as the transition stage, moving from a protoplanetary disk to a solar system-like structure. So, the perfect disk subject was found. It was time to track some neon, a peculiar gas great for disk exploring. It's one of the gases that are more likely to exist in protoplanetary disks. Plus, neon spits out electrons at pretty modest temperatures, which makes it easier to spot. After examining the region with the help of the JWST, scientists concluded that neon was indeed coming from further away from the star. But that was not all. Along with neon, the team found argon. It has been seen in several protoplanetary disks before, but its traces have never been this strong. Some senior researchers thought it wouldn't be possible to see them so clearly, but thanks to James Webb, and after vigorous tests, the results were confirmed. These results are a small but crucial step in understanding more about the mind-boggling nature of gas planets.
The James Webb Space Telescope, an astounding piece of equipment built to outperform the Hubble Space Telescope, has made a terrifying and amazing discovery that might completely change our perception of the universe. It has successfully detected a faint glow coming from a staggering 7 trillion miles away. Can this glow be shining city lights coming from some mysterious extraterrestrial world galaxies away from us? Well, let's start from the beginning. A few years ago, NASA's Infrared Spitzer Space Telescope helped us spot a family of 7 rocky exoplanets orbiting the same star. This star is known as TRAPPIST-1. And recently, our new infrared powerhouse, the James Webb Telescope, has measured the temperature of one of those distant worlds. It was a planet called TRAPPIST-1b. Unfortunately, it turned out that this Earth-like planet was totally uninhabitable. Astronomers took James Webb's mid-infrared camera, called MIRI, and looked at the planet's thermal emissions. We can picture the whole process as scientists using heat-sensing Terminator vision. The results were quite disappointing. TRAPPIST-1b turned out to be scorching. Its average temperature was around 450 degrees F. That's as hot as in an oven. Plus, the planet most likely doesn't have any atmosphere. At the same time, this discovery was another record-breaking first for the telescope, which had already produced some newsworthy results by that time. It was the first time researchers detected any form of light emitted by a small and relatively cool exoplanet similar to the rocky planets in our own solar system. No previous telescope had enough sensitivity to measure such dim, mid-infrared light. When 7 TRAPPIST-1 exoplanets were first discovered, the astronomical community was ecstatic. That's because all those faraway worlds were about the size of our home planet and located in their star's habitable zone. It's the region that is just the right distance away from a star for liquid water to exist on a planet's surface. Thus, the planetary system became the best place to look for rocky planets with an atmosphere. But don't get too excited yet. These planets aren't likely to become new worlds for humans to explore, mostly because the TRAPPIST-1 planets are totally out of our reach at the moment. They're just too far away, at a whopping 235 trillion miles away. Their star is also much smaller and redder than our Sun. It's classified as an M-dwarf star. In our home Milky Way galaxy, there are twice as many of such stars as there are stars like the Sun. and they're also twice as likely to have rocky planets orbiting them. It's probably not surprising that astronomers are very interested in such stars. They're the main targets for seeking potentially habitable planets, and it's also way easier and more convenient to observe rocky planets around such smaller stars. But there's a catch. M dwarfs are more active than our Sun. They frequently flare and spew high-energy rays which are likely to be extremely damaging to planets' atmospheres and any forms of extraterrestrial life. When researchers examined TRAPPIST-1b before, their observations weren't sensitive enough to determine whether this world had an atmosphere, or if it was just a barren rock. But now, we know. The planet is tidally locked to its star, which means that one of its sides always faces the star, while the other is stuck in perpetual darkness. The latest simulations suggest that if this planet had an atmosphere, its temperatures would be much lower since the air would redistribute the heat around both sides of the planet. Unfortunately, the James Webb Telescope recorded much hotter temperatures than needed for such a favorable scenario. It indicates the absence of an atmosphere and knocks the planet off our list of possibly habitable worlds. But the main excitement here isn't actually the features of TRAPPIST-1b. The main takeaway is that James Webb is capable of making such kinds of measurements. It'll help us explore the atmospheres and temperatures of many other distant worlds.
The James Webb Space Telescope has recently discovered the oldest black hole ever found. It's an ancient monster as massive as 1.6 million suns, and it's lurking 13 billion years in the past at the center of an infant galaxy. This supermassive black hole appeared a mere 440 million years after the beginning of the universe. But it's just one of the countless black holes that inflated to terrifying scales during the dawn of the cosmos. It's the period about 100 million years after the Big Bang. That's when the young universe started to glow for a billion years. This discovery of the universe's oldest black hole can provide astronomers with the answers to some vital questions. For example, how could these space whirlpools balloon in scale so fast after the universe began? Or how did they appear in the first place? You see, black holes in the early universe couldn't grow as quietly and steadily as many modern black holes do. They were bound to experience some peculiar formation and growth. At the same time, closer to the present day, black holes are believed to be born from the collapse of ginormous stars. They grow by munching on gas, dust, stars, and other black holes non-stop. The friction created in the process makes the material, spiraling into a black hole, heat up, and it emits light that can be detected by our telescopes. To spot the oldest black hole, scientists used two infrared cameras, the JWST's mid-infrared instrument and near-infrared camera. They used the camera's built-in spectrographs to break down the light it had been recording into its component frequencies. While examining the results, they discovered unusual spikes among certain frequencies. It could only mean that the hot material around a massive black hole was beaming out faint traces of light. One of the most popular explanations for how ancient black holes grew so rapidly is that they appeared after sudden collapses of colossal gas clouds. Or they could form as a result of merges between clumps of stars and black holes. There's also a possibility that some of the oldest black holes could have been seeded by hypothetical primordial black holes. Those are believed to have appeared moments after the universe began, but their existence hasn't been proven yet. In any case, this most recent finding of the ancient black hole is extremely important because the formation of galaxies and the appearance of black holes go hand in hand. Every normal-sized galaxy that we know of has a black hole at its center. But even though such black holes are massive and can weigh millions and billions of solar masses, they are still tiny in comparison with their home galaxies. A supermassive black hole usually reaches less than 1% of the mass of a regular-sized galaxy and has a volume that is billions of times smaller. And still, somehow, supermassive black holes can influence galaxies, controlling the formation of stars for billions of years. The thing is, black holes exert an enormous gravitational pull on their surroundings. Any gas, dust, and stars that come too close to a black hole find themselves trapped. A lot of material crams into the space around the black hole and heats up, because that's what materials do when compressed. Soon, everything around the black hole flattens into a thin disk, which is called the accretion disk, and starts swirling around the black hole. Astronomers believe that this process is behind the mysterious relationship between black holes and their host galaxies. It's a connection between the mass of the supermassive black hole and the velocity dispersion of the gas in the galactic core. This cycle also controls the rate of star formation, which is a crucial element of the evolution of galaxies. If this delicately balanced process goes off kilter, the outflows from black holes can get too strong, not only heating the gas in a galaxy, but also removing it altogether. And then, the formation of stars doesn't simply slow down, it stops completely. Major galactic merger events can lead to such dramatic consequences because too much material falls into the central black hole too fast.
The Hubble and James Webb Space Telescopes cooperate to explore space. Their observations complement each other and provide us with a broader view of the universe. But there are some significant differences between these two space explorers. Let's compare them. Currently, James Webb is the largest and most technically advanced telescope we've ever built. It can peer back over 13.5 billion years, observing the first stars and galaxies forming in the darkness of the early universe. The telescope's infrared vision cuts through massive clouds of gas and dust where planetary systems and stars form. This ability goes way beyond Hubble's infrared view, used for studying distant exoplanets. Hubble can actually observe space in near-infrared light, but it was optimized for shorter ultraviolet and visible wavelengths of light. This difference is what makes Webb and Hubble an awesome pair of observatories covering a broad wavelength range. Both Hubble and Webb are reflecting telescopes, which means that they use curved mirrors instead of lenses to gather and bend light to their numerous instruments. And still, these two have some obvious differences. Hubble observes the universe from an orbit just above Earth's atmosphere. That's why it needs to block stray light coming from the sun, as well as sunlight reflected by Earth and the Moon from entering the telescope. To accomplish it, the forward assembly of the observatory is wrapped in an insulated, aluminized Teflon light shield. This gives the telescope its tube shape. As for James Webb, it has a large, multi-layered sun shield that looks nothing like Hubble's light shield. And still, it serves the same purpose. Webb's primary mirror, which is more than 21 feet across, is way larger than Hubble's 7.9-foot one. No wonder Webb has more than 6 times the light collecting area that Hubble has. It's very important at the longer and dimmer wavelengths of light James Webb sees. You see, the universe is constantly expanding, and light from distant objects gets stretched when it travels to Earth. Shorter, bluer wavelengths of light stretch toward longer, redder wavelengths. That's why distant objects that look bright in blue or ultraviolet light turn red or redshifted once their light reaches Earth. They also get way dimmer. Webb's primary mirror gathers more of this dim, redshifted light, giving us clear views of objects 100 times fainter than what Hubble can see. Hubble is optimized to see ultraviolet and visible light. That's why its primary mirror doesn't need to be as cold as Webb's. More than 200 thermal sensors keep Hubble's instruments at optimal temperatures. An array of heaters warms the back of Hubble's primary mirror. That's where the observatory's science equipment is located. This part needs to be stiff and thermally stable. So Hubble's heaters maintain a temperature of 70 degrees F. As for Webb, it needs to be much colder than Hubble to capture those faint infrared wavelengths of light. The problem is, unlike visible light, we can't see infrared light with our eyes. But we can feel it because it's heat, or thermal radiation. When you turn your face toward the sun, you feel warmth. That's what thermal radiation is. To be able to capture the remains of the heat from objects so insanely far away, Webb needs to be extremely cold, minus 364 degrees F. To maintain this temperature, the telescope needs to shield itself from the infrared radiation coming from the sun, Earth, and the Moon. That's why it has to be way farther from our planet than Hubble. Hubble orbits Earth 326 miles above the surface of the planet, but Webb orbits the Sun with Earth around 1 million miles away from home. From its perspective, the Sun, Earth, and the Moon are always in the same part of the sky. It allows the observatory's enormous sun shield to block the light coming from these space objects and keep the telescope cool. The gravitational forces of Earth and the Sun also make it convenient and easy for the telescope to hold its orbit. Webb only needs an occasional modest rocket thrust to keep its steady orbit. As for Hubble, due to its close proximity to Earth, it needs to deal with a dent in our planet's magnetic field. This dent is called the South Atlantic Anomaly, and it collects charged particles from the Sun. It tends to cause communication disruptions and problems with electrical systems. Hubble has to pass through this region 10 times every day, staying there for nearly 15% of its time. It took a lot of time for the light emitted by several incredibly old galaxies to reach the James Webb Space Telescope. After scientists made more precise estimates, it turned out that the photons had been on the way for over 13 billion years. That's about as long as the entire history of the universe, and only recently have they reached our orbiting observatory. These dramatic results have revealed that the universe started creating stars almost immediately after the Big Bang. But if you look at the images delivered by the James Webb, you won't be overly impressed. Just a handful of smudges, a few glowing spheres, and something resembling a dog bone. And still, the world of astronomy has been left speechless. The telescope's giant mirror has managed to capture the oldest known galaxy in the entire universe. The galaxy got quite a prosaic name, mostly consisting of letters and numbers. Yeah, that's rather catchy. It appeared a mere 320 million years after the Big Bang. In comparison with our home galaxy, this ancient one was tiny. But after its birth, it started vigorously producing new stars at a rate comparable to that of the Milky Way. Interestingly, the Webb telescope has managed to photograph a few other ancient galaxies that had the same characteristics. Based on the snapshots of the baby universe we've got, we can conclude that in those ancient times, the first galaxies and stars were evolving amazingly fast. They also appeared much earlier than most scientists thought. Now, let's talk about the hero of the day, the outstanding telescope itself. The James Webb Space Telescope is a stunning piece of equipment. It's around 100 times more powerful than the Hubble Space Telescope, and the latter has observed places that are 13.4 billion light-years away. The James Webb Telescope is also on the pricey side, to put it mildly. Even though originally the cost of the telescope was estimated to be just $1 to $3.5 billion, the entire process of its construction cost around $10 billion. For comparison, NASA spent $4.7 billion to build and launch the Hubble telescope, and it was another $1.3 billion to fix it in orbit. Even though the James Webb Space Telescope itself is 3 stories high and the size of a tennis court, its mirrors are the lightest large telescope mirrors of all time. No wonder, during the manufacturing process, they underwent a 92% reduction in weight. The lighter, the cheaper it is to send stuff to space. If you had a chance to look at these mirrors, they would seem to be gold, but they're made of beryllium. This is a steel gray, lightweight, and brittle metal. A gold coating is still applied to each mirror, but they can't be produced entirely out of gold since this material needs to expand and contract even with small temperature changes. And that's not what we need to happen to a super precise piece of equipment. That's why the total amount of gold used in the construction of the James Webb Telescope is less than 2 ounces. That's a golf ball-sized chunk of gold. The gold plates covering the mirror are only 1,000 atoms thick. If we speak about all those incredible feats the telescope is capable of, it can clearly see a U.S. penny from 24 miles away and a football from 340 miles away. Hey, what's the score? JWST comes with significant advantages over any previous mission. For example, its 21-foot mirror is composed of 18 gold-plated hexagonal segments. They gather more than 6 times as much light as the Hubble Space Telescope's almost 8-foot mirror. It means that James Webb can record light from all kinds of space objects 6 times faster than its predecessor. The telescope's sensitivity to infrared light is also astonishing, which is remarkable since it can see different things than optical telescopes. You can say it's a real game changer. The James Webb can observe wavelengths from 0.6 to 28.5 micrometers, from the red end of the visible spectrum to the mid-infrared. As for Hubble's optics, most of the telescope's sensitivity is centered on visible light. It might sound surprising, but in its intended infrared domain, the Webb telescope isn't likely to resolve finer details than Hubble can detect in optical light. The thing is that although resolution increases with the mirror size, it also diminishes with wavelength. James Webb's telescope side cools itself down because otherwise it might get damaged or even burned. Normally, its temperature doesn't rise higher than minus 370 degrees Fahrenheit. That's cold enough to make hydrogen liquid. An enormous 5-layer sunshield surrounds the telescope and reflects as much sunlight as possible, letting the telescope stay cool. The telescope was launched near the equator because Earth spins a bit faster there, and this gave the rocket some extra push. When the James Webb Space Telescope runs out of fuel, it'll just keep orbiting the Sun. On the other hand, even though the telescope wasn't designed to be serviced or upgraded, it might potentially be refueled with the help of robots in the future. This might extend its lifespan. Anyway, here are the reasons why we can say this telescope has changed astronomy. For one thing, we might finally see dark matter. Around 84% of matter in the universe doesn't emit or absorb light. Astronomers call this stuff, which can neither be seen directly nor detected by indirect means, dark matter. It affects visible matter, radiation, and the very structure of the universe. Dark matter is like some binding agent of our universe, and we're still not sure whether it exists. And now, thanks to the James Webb Telescope, scientists might finally have a way to seek dark matter. It's a huge development that is likely to change the way we observe the known as well as unknown universe. Even though astronomers haven't seen dark matter directly yet, they have been able to trace the distribution of this mysterious universal compound, all thanks to James Webb's powerful instruments. Another reason the new space telescope is so cool is that it helps us learn more about star formation. This process has always been a foundational part of astronomical studies. But even though Hubble has provided us with some iconic images and observations, there are still many unanswered questions about how stars form and go out. But astronomers are sure that James Webb will fill in the blanks. All because this telescope can peer further and deeper into the universe than any other telescope that has ever existed. Its location and cutting-edge equipment allow it to gaze through gases and dust surrounding early galaxies and stars. It will let us get a better look at star formation. It's also obvious that Webb's discoveries are bound to change the way we think of the early universe. For example, recently, the telescope has revealed several large galaxies that scientists believe existed not long after the Big Bang. They aren't supposed to be there, and no one expected to find them. And still, the James Webb Space Telescope has spotted them. These 6 galaxies, as massive as our home Milky Way, are full of mature red stars. Astronomers have analyzed the light coming from them and estimated their age 5 to 700 million years after the Big Bang. The most bizarre thing about these galaxies is their tremendous size and the age of the stars inhabiting them. This information doesn't coincide with the existing ideas about what the universe looked like and how it evolved in its early years. Plus, it doesn't match the earlier observations made by Hubble. Astronomers hope that one day, James Webb will help us find new exoplanets and even detect water there. For a long time, astronomers have been discovering planets orbiting stars outside the solar system by monitoring slight dips in stars' light. Such dips happen when planets pass in front of them, and reading unique signatures in the light can tell us about planets' chemical composition. The strongest and most readable signatures happen within the infrared spectrum. Have you just thought of James Webb's state-of-the-art infrared instruments too? They can help scientists spot new planets and even identify the presence of water there.
The James Webb Telescope, or JWST, is like the ultimate intergalactic paparazzi. It takes pictures of some of the most famous celebrities in the universe. Stars, galaxies, exoplanets, you name it. The James Webb Space Telescope will snap a photo. So if you're a fan of cosmic celebrities, let's take a look at some of these best star-studded photos. The Carina Nebula. The image of the nebula with the beautiful name Carina was published on July 12th. JWST captured a beautiful view of the nebula, located about 7,500 light-years from Earth. Nicknamed the Cosmic Cliffs, it is, in fact, a hotbed of young stars, some of which are several times larger than our Sun. The Carina Nebula is a celestial spectacle located in the southern constellation Carina. It's really huge, approximately 260 light-years across. Massive stars within this nebula are so bright and hot that they create a glowing cloud of gas and dust around them. The Carina Nebula also contains swirling clouds of gas and dust where new stars are being born. The gas collapses under its own weight, becomes hotter and denser, and all this eventually leads to the creation of new stars. However, the Carina Nebula isn't just some peaceful place of star formation. It's the site of some of the most destructive events in the universe, which create massive shockwaves that obliterate everything in their path. Very chaotic and cool. The Stephan's Quintet. This photo was also posted on July 12th. Stephan's Quintet is a visual group of 5 galaxies located at a huge distance from us. About 290 million light-years in the constellation of Pegasus. It's like a cosmic family reunion. All these galaxies are related to each other and interact with each other in some interesting ways. They're pulling and tugging on each other with their gravity, constantly exchanging gas and dust. This interaction is causing some of the galaxies to collide and merge, which can create all sorts of cool effects, like bursts of star formation and supernovae. Thanks to JWST, we were able to see shockwaves, tidal tails, and other amazing details about these galaxies. Their interactions create a stunning sight that we can see in this photo. Jupiter. And here's our old giant friend. This image was published by NASA on August 22nd. Jupiter is the largest planet in our solar system, and it's known for its many moons and its beautiful swirling clouds. But it also has a system of rings, just like Saturn, which are made up of tiny particles of dust that orbit the planet. These rings are much smaller and less visible than Saturn's, but they're still pretty neat. Jupiter also has auroras, which are colorful light displays that occur in the planet's atmosphere. They're caused by charged particles from the solar wind interacting with Jupiter's magnetic field. Just like on Earth, they can be seen near the poles of the planet. But these auroras are much brighter and more intense than ours. We can even see this crazy light show from space. And now, we were finally able to capture this dazzling sight. JWST's photo shows the auroras of Jupiter, its rings, and even 2 moons, Amalthea and Adrastea. It's amazing how bright and clear they are on this photo. The Cartwheel Galaxy. NASA released this image on August 2nd. This photo shows us the Cartwheel Galaxy and its companions. The Cartwheel Galaxy gets its name from its shape. It kind of looks like a cartwheel, doesn't it? This is a giant swirling mass of stars, gas, and dust, which is located in the depths of space. It's shaped like a pinwheel with long spiral arms. These arms are held together by the gravity of the central region, which is home to a supermassive black hole. But the Cartwheel Galaxy is a bit different from its spiral relatives. It has formed when a smaller galaxy collided with a larger one, creating a shockwave that rippled through the gas and dust. We'll definitely have to visit this galaxy someday. It's sure to be a wild ride. Spiral Galaxy M74. And here comes another spiral galaxy. NASA released this image on July 22nd. JWST had to peer through thick layers of dust and gas to see this beautiful star cluster. M74 belongs to a special class of spiral galaxies known as the Grand Design Galaxy. This means that its spiral arms are noticeable and clearly outlined. All sorts of amazing things are happening inside of spiral galaxies. Supernovas, stars being born in clouds of gas and dust, and many other cosmic wonders. The glowing gas and dust, the bright stars, and the swirling patterns of the spiral arms make them some of the most striking objects in the universe. Well, we can clearly see it on the example of M74. The Tarantula Nebula. This image of the nebula with a creepy name Tarantula was published on September 6th. The photo covers as much as 340 light-years across. This is a huge distance. Thanks to this image, astronomers have discovered new young stars that were previously shrouded in dust. The Tarantula Nebula is located 160,000 light-years away from us, in the Large Magellanic Cloud. It's the largest and brightest star-forming region in the local group, the galaxies nearest our Milky Way. It's named after its shape, which looks like a bit like the legs of a big tarantula. It's a vast region of space, about 1,000 light-years across, and it's home to some of the most massive and luminous stars in the universe. One of the reasons why the Tarantula Nebula is interesting to scientists is its composition. Its composition is close to the region of stars of the cosmic noon, the so-called state of our universe when it was only a few billion years old. At that time, star formation was at its peak. Thanks to the Webb telescope, we can study this galaxy better and find out what our universe was like at its peak. Neptune's rings. This photo was published on September 21st, 2022. In this photo, we can even see 6 small moons next to the planet, with Triton shining brightly in the upper left corner. You didn't think it was the sun, did you? And yep, Neptune has rings too. They're like the ultimate cosmic accessory. They add a touch of glamour and style to the planet. But unlike some earthly bling, these rings are made of small particles of dust rather than diamonds and gold. There are 5 known rings around Neptune: the Gall, Leverrier, Lassell, Arago, and Adam's rings. Scientists think that these are relatively young, much younger than our solar system, and much younger than, for example, Uranus's rings. They were probably created when one of Neptune's inner moons got too close to the planet and was torn apart by gravity. We haven't seen Neptune's rings so brightly since Voyager 2 flew past it back in 1989. So this is a great opportunity to take a closer look at these rings. The Pillars of Creation. This photo was published on October 19th. The Pillars of Creation became famous thanks to the Hubble telescope, but this photo is very lush and much more detailed. These columns, located in the Eagle Nebula, are about 5 light-years tall, which is really, really long. And they look like some majestic rock formations, only much more transparent. Just like a typical Hollywood movie set, they're full of action and special effects. They're home to some of the most dramatic processes in the universe. The gas and dust are collapsing under their own gravity, forming clumps that will eventually become stars. The place is full of intense radiation, jets of high-energy particles, and supernovae. It's like a cosmic version of Survivor. And if this wasn't creepy enough, here's another photo published by NASA on October 19th. They shared it right before Halloween. Here, the pillars resemble an eerie hand reaching for something. Brrr. Anyway, all these photos give us a truly awe-inspiring sight. They remind us of the incredible complexity of the universe and the amazing things that are happening even in the darkest and most remote corners of the cosmos. Let's hope that the James Webb Telescope will continue to amaze us in the future.
Wow, the James Webb Telescope has been fully deployed. If you're interested in astronomy or space, you've got to be excited about the James Webb Space Telescope. Here's why. For starters, it's huge. How huge? The primary mirror of the JWST is over 21 feet wide. The Hubble Space Telescope, the previous largest eye in space, has a mirror of about 7 feet 10.5 inches. By comparison, if you place the two telescopes side by side, it'd be like putting a horse next to an elephant, and elephants are enormous. There's a perfect reason why the Webb, as it's affectionately called, is massive. It has to be huge because it's not an optical telescope in the traditional sense that most telescopes are. The JWST is an infrared telescope. It sees heat. Infrared light has a longer wavelength than visible light, so it needs a larger mirror to focus that light. So what do we have here with the James Webb Space Telescope? We have two never-before things going on. We have incredible technology and incredible science missions. Both the missions and the technology are out of this world cutting edge. The Webb is a classic example of engineering in the service of science. Because of its greater light gathering power, the James Webb Space Telescope will be able to take images of things that we were never able to see before, but have always wanted to see. Things like exoplanets and the first galaxies in the universe, and stars and planets forming inside nebulae. And you can bet that there will be plenty of surprises too. The James Webb Space Telescope has several technological tricks up its sleeve, which promise to provide its greatest scientific discoveries. The Webb has a coronagraph, and a very special coronagraph at that. The coronagraph is the tool that will allow the first real pictures of exoplanets. The coronagraph blocks out the bright pinpoint light of stars, which we already know have planets orbiting around them. Without the coronagraph, the starlight would make things too bright to see these planets, because planets are hundreds of thousands of times dimmer than the star. But with the coronagraph blocking the starlight, the exoplanets come into view. And the JWST coronagraph can block the light from up to 100 stars at once. We can expect a swarm of exoplanets. This brings us to the next high-tech gadget the JWST has up its sleeve, a no-slit spectrograph. Usually, an ordinary spectrograph will have a slit to allow a sliver of light to enter and be diffracted. Diffraction is the scattering of light to reveal the spectrum of the light's component wavelengths. But the James Webb Space Telescope's work is so sensitive that a sliver of light would overwhelm the optics. So a no-slit spectrograph was installed. The starlight gathered from the big mirror is sent into a fiber optic cable to send only a single spot of light into the spectroscope. And that's where the grism takes over. Sir Isaac Newton used a prism to discover the spectrum of sunlight, Roy G. Biv, as you may recall. But the Webb uses a grism. That's a compound word, like smog, which is smoke and fog. A grism is a graded prism. That means it has itsy-bitsy, teeny-tiny grooves that diffract the spot of light the big mirror sends down the fiber optic cable and into the spectrograph. The science of reading a spectrum of light is called spectroscopy. By analyzing the spectra of light from the exoplanets, the JWST will determine what gases are in the planet's atmospheres, as well as their density and even their temperature. It's an incredible advance in our knowledge. We'll be able to tell if a planet has oxygen or nitrogen, or methane, and other gases that may or may not indicate that the planet is habitable. Another Earth, perhaps. Presently, the JWST is parked in its permanent location. Unlike the Hubble Space Telescope, which orbits the Earth, the James Webb Space Telescope orbits the Sun. It orbits the Sun at one of the gravitational balance points between the Earth-Sun system. It just stays there without having to use much or any fuel to hold its position. So, as the Earth orbits the Sun, the James Webb remains parked at a spot that is also orbiting the Sun. There are 5 gravitational balance points between the Earth and Sun. They are called Lagrange points, after their discoverer, Joseph Louis Lagrange, in the 18th century. The Webb is parked at L2, the second of the 5 Lagrange points, which lies 932,000 miles out into space, way beyond the Moon. All this to observe a spot of infrared light. But first, the engineers must get, or acquire, that spot of light. To get a spot of infrared light, the 18 hexagonal mirrors had to be unfolded from their position inside the Ariane rocket that sent the Webb into space. Once the mirrors have unfolded, their positions must be adjusted to microscopic level accuracy so that all 18 mirrors produce a single image. Several tiny motors are attached to each mirror segment to make these adjustments. These motors, which must be activated individually, will gradually pull the honeycomb-like mirror segments into alignment. It's a critical part of the mission and takes months to complete. To align the mirrors to produce a single spot of light, the James Webb Space Telescope can't be jiggling around. The telescope must be kept absolutely motionless, and that requires two other cutting-edge technologies, the sun shield and the cryocooler. In space, direct sunlight is very hot, and shadow is very cold. Therefore, the James Webb Space Telescope brought along its own high-tech sun shield. It's huge, too, as big as a tennis court huge, comprised of 5 individual layers of Kapton film, only a millimeter thick. Each layer of the sun shield has to be remotely deployed individually using a system of 8 motors and 139 actuators with thousands of parts. The purpose of the sun shield is to help the JWST stay cold. The colder the better. And colder is what the cryocooler is for. Temperature can be measured 3 different ways: in degrees Fahrenheit, where water freezes at 32 degrees and boils at 212; in degrees Celsius, where water freezes at 0 degrees and boils at 100 degrees. But neither of these thermometers have a starting point. So, Lord Kelvin, in the 19th century, devised a third temperature scale, the Kelvin scale, which starts at absolute 0, the coldest temperature possible. The onboard cryocooler will cool the JWST to just 7 degrees Kelvin, 7 degrees above absolute 0. At this temperature, virtually all heat from motors is removed, and the telescope will be able to focus the light to a point without any noise, basically any motion interfering with the quality of the image. Finally, after all this incredible technology functions remotely as planned, we are almost ready to observe the infrared images from the giant multi-segmented mirror of the James Webb Space Telescope. Almost ready. A telescope can collect all the light it wants, but in the end, it must also be able to detect what it's collected. If the light is not detected, it's not truly observed. Enter the pièce de résistance, the infrared detectors. The Webb has 15 of them. The specially fabricated semiconductor material produces a slight electrical charge when struck by a photon of infrared light. The Webb's infrared detectors can produce a 1,000,000-pixel high-def image. A few of the detectors can produce a 4,000,000-pixel image. They must be durable enough to last 10 to 20 years without warping or corrupting, all while working at 7 degrees above absolute 0. In themselves, the infrared detectors on the JWST are an engineering marvel. But what are they going to take pictures of? The missions of the JWST. Well, they're cutting edge too. 70 of the first 280 target observations are exoplanets. Is there another Earth? Which exoplanets seem habitable? The Webb telescope will provide detailed spectroscopic analysis of the atmospheres of thousands of known exoplanets. For the first time, we will see images of exoplanets as they appear in infrared light. Cosmology, the study of the universe, is perhaps the primary mission for the Webb. Galaxies receding away so fast that their light is stretched into the infrared will be a prime target for observation. Hundreds of hours of observations are necessary to collect the faint infrared light from these first galaxies formed after the Big Bang. The JWST will give us a picture of what the infant universe looked like. Astronomers will learn new information about the dark energy that is driving the expansion of the universe and what role, if any, black holes play in the formation of galaxies. Star formation in the Milky Way and nearby galaxies is also part of the mission of the James Webb. By imaging hundreds of solar systems forming around newborn stars, astronomers will establish a definite history of solar system development. Now fact will replace theory, and a big step forward will be taken in our understanding of space. The James Webb Space Telescope is a bold endeavor that will mark an epoch time in scientific history.